chug, there's a couple ways we can word it. Either we give you 2 temperatures and 2 pressures. That would be a pretty common style. And then you know it's one of these, so there's 2 states involved. The other way we could do this is to give you a temperature and ask about the pressure, but we don't give you the other temperature and pressure, and that's because we assume you would know it. So a classic example would be water. We think you would know that at 100 degrees, the pressure would be atmospheric pressure. So that's a free data point always for water. So you know that pressure would be 1 atmosphere, temperature would be 100 C. And so that'd be a free data point. And then we would just say, what is the vapor pressure of water at temperature whatever. Okay? But usually, we're giving you 2 temperatures and 2 pressures. I would encourage you, I don't know if I'll be able to find it in this short amount of time, but in the reader, when you take a look at it, there are several points where I mention common mistakes, common issues that people have when they're doing the Clausius-Clapeyron. So look in that section of the reader, it's somewhere. Okay? That's all I really have to say about the Clausius-Clapeyron. Plug and chug, pretty much. Let's do hydrogen bonding. The force. As you increase the force, then you know several things happen. Will the boiling point go up or down? How about the viscosity? Up. The vapor pressure? Down. And there was something else. Surface tension? Yeah, the surface tension goes up. So hydrogen bonding is one of these. It is a very strong dipole. It needs to happen between a hydrogen to a nitrogen, oxygen, or fluorine. These need to be on typically 2 separate molecules. So for example, water would work. Here's water. But it would need another, you need 2 total waters for this to happen. So it'd be, say, between this hydrogen and that oxygen as an example. Okay? So that'd be hydrogen bonding. It is, per force unit, the strongest. The only way that it can be overcome is, say, by the London force having a very large molar mass for a compound. The London force can overtake it. Any particular questions that people had on H bonding? Okay? Okay? H bonding. Let's look at the calorimetry. This would be I guess several of these categories could be, depending on how the question was worded, a short answer or a long answer sort of question. For the calorimetry question, the coffee cup versus the bomb. The bomb is a little bit more straightforward. The bomb, would just say Q is going to be negative, so Q of reaction of sorts is negative C delta T, which comes from this derived initial thing, the sum of the Q's equals 0, but this always shakes out to be this. This equation, though, depends on the number of items you have in the system. You need to distinguish between things that are enthalpy and temperature changes. The temperature changes are usually easier to recognize if something changes the temperature. You need to watch out, though, if anything goes through a phase change, a reaction occurs, or a solution is mixed. If any of those 3 happen, usually there's a delta H involved, and so then your Q would be one of those. So let's change colors here. If it's this sort of thing happening, Q is mCp delta T. So you need the mass, the Cp, and the delta T. If it's one of these, then I usually say Q is N delta H. It can be a little bit varied. It depends on the delta H. I need to zoom in so I can point at it. The delta H is usually in kilojoules per mole, so you need to multiply by moles or N. Get rid of the mole unit, and then you'll have Q. Often, because delta H is in kilojoules, you'll need to convert to joules in order to use it together with this equation and to sum up this equation because this one's often in joules. Was there a particular question on this? I'm happy after I dismiss people who want to go, when we do specific questions, if you have examples of these, we can do those together. The sum of the q's equals 0? Oh, that's it? Okay, good. We have a couple minutes. Let's do Raoult's law, unless there's a question on it. Raoult's law, another classic, can be a long answer or it can be a short answer sort of question. First, a little summary about what is Raoult's law. Let me flip over and let's look at the picture of this that I have in the reader. This is on page 46. And let's do this so I can write on here. So this formula is going to be the partial pressure is the mole fraction times the total pressure. That's Dalton's law. Raoult's law will be PA, XA, PA naught. So let's say the compound's A. All right, let's kind of go through some of these. Are these partial pressures referring to the same thing? Yes, good. We covered this. What is it referring to? They are the partial pressures above the solution. In fact, above the solution is the only place that a gas exists. So it's talking about whatever the pressure is of A in the gas state, right above the liquid. That's what PA is. What's the thing that's not the same? Yeah, you might be confusing the pressures with the mole fractions. The mole fractions are the things that are different. So you could actually set these equations equal to each other, if need be, in a particular problem, because the PAs are equal. The X's are not the same, even though they're both X's. The X on the bottom refers to the mole fraction in the solution. The X up here for Dalton refers to the mole fraction in the gas above the solution. Okay, one more time. That sounds exciting for people. This mole fraction is the mole fraction of the liquid. This is the mole fraction of the gas. Those would rarely be equal, but it's possible they are. But usually the mole fractions are never equal in here versus up here. Okay? This is the partial pressure of the pure solution, so only A. And this is the pressure total in the solution. Okay, so it's the total pressure above the solution, including A, B, C, whatever components are involved. So this can go multiple ways. You can have a question just about Raoult's law. You would not have a question just about Dalton's law without Raoult, because Dalton was really Chem 2A. But you could have a question that involves both of them. So a couple other notes. Oh, they're up here at the top of this page. Remember that the sum of the mole fractions will equal 1, and the sum of the partial pressure is equal to total pressure. Okay? And this one specifically includes Raoult's law, so you see Raoult's law here. Dalton's law is the one written right there. So you need to read prepositional phrases correctly. If we ask for the mole fraction above the solution, we're asking you to use Dalton's law to find that. If we're asking for the mole fraction in the solution, we're asking you to use Raoult's law in some way. Yes? Do you need Raoult's law to find something in Dalton's law? The way a classic problem is set up in 2B, I would say yes. Usually the Raoult's law problem would precede the Dalton's law problem. I don't have the question we did in class that day, but we did a long answer question that had, I believe, 7 parts. And if you look back at it, we did the Raoult's law part first, and then went to the Dalton's law part, because We were given the masses, and we were able to find this by changing to moles. Find this in solution. We were given the pure pressure, so we can find that. So we found this in the first half of the problem. That's pretty classic. Then we plugged it into here, and knowing the total pressure, we were able to find this. So remember that you can set these equal to each other because these partial pressures mean the same thing. The mole fractions don't mean the same thing. So again, a classic problem is to use this first, say to solve for a partial pressure of A, and then plug it in up here to solve, say, for the mole fraction, pretty typically. Okay? All right.